What happened to the days when C's are big deals? Okay, let's go a couple of examples that are going to have two questions with multiple things. Question number one, guys, I have a delta Y transformer. Here's my delta, and you're going to find it easy because you guys are sharper than a tick. I'm going to call this is question number 8, starting with an A here at the top. And my second one is a Y, okay? And don't forget that this is all in a big fat box, as they should. And I need to find fuses and circuit breakers and so forth for this system. So I want to remind you guys, this is I primary, this is I, oops, this is I secondary. We just started, Nick. And I have the voltage on the primary is 480 volt. On the secondary side, I'm pulling, what am I pulling here? I should be pulling 208, 120. Can't pull 240, 120 in the system. What do you look at, Chad? I'm pulling 208/121. Okay? And the size of this baby is 1,000 kVA, and the impedance is 4%. The impedance is 4%. Okay? And don't forget that we need to bond and ground this baby right here. It is a grounding conductor. And we're going to find a few things for this baby. Don't forget that we guys have always fuses on the primary, fuses, and also on the secondary fuses, fuses or circuit breakers. So we have fuses and circuit breakers on the primary and the secondary. We need to size them. We've done that before, so that shouldn't be a big deal. Any question, guys? Transformer, primary, secondary, and size the following for it. Any question about the given? 482.77, 1,000 kVA, 1 meg, and we need to size the information. I need somebody's calculator handy here. That's question number 1. Has 10 things that we need, 11 things that we need to find from it. 11 things, very easy, simple, piece of cake. Oh, you don't believe me? Who's that? Oh, people, I thought you trust me. Number 1, the first thing we need to find is, guys, prime current. I need to find the primary current for this baby. The primary current. The primary current, if you guys remember before the holidays, I primary equal the kVA of the system, which is 1,000 K, divided by 1.73 multiplied by the voltage on the primary side, and that will get you a healthy 1204 amps. I don't know if I did that right. 1204 amps. Okay, so that's a primary this is primary current, and next to it, guys, could you please say line? Primary current, line, the line current. Piece of cake. The second one, I need primary current coil. You guys remember the coil from Gary's days? Coil. The coil is right in here. I coil. So I'm asking you to find I primary. The first one was line. The second one was I primary coil. I primary coil. If you guys, it's a delta. So remember, the line current is always 1.73 times the coil current. The current inside the delta is always less than the current outside that's coming to the delta by 1.73, divided by 1.73. So the formula is piece of cake. I primary line divided by 1.73. Take this 1204 divided by 1.73, and you are lucky if you get 696 amps. Done. Everybody knows what the line. I hate to even. The most important one, guys, is a line current. Moving on, you would never hear me saying about the coil. Always a line current. The coil is for people who manufacture the transformers. They need to know how much current these leads are going to be. We don't manufacture transformers. We install them, so we need the line current. Any question about this? Oh, that's a piece of cake. Up to this point, let me know when I can move. So now, if you're going to move ahead, we're going to do the line current on the secondary and the line current and the coil current on the secondary. So that's it. Can I move when can I have heads up, down? Good there. Good there. Good. Chris?
On this 2 currents, which one is the first current?
The coil is the phase. Yeah. You call it the coil or the phase current. The coil current. Okay, number 3. Number 3 is a very piece of cake. When you do the secondary current, but this time we're going to do the line, and I do it in a red just to emphasize it. Line. The line current in the secondary piece of cake, Chad. I secondary line equal the same 1000K divided by 1.73 times. What's the voltage on the secondary out before? 2.8. And I did not do this math. I did it on a different system. How much? 2. Thank you. 2062. Please tell me you didn't do it in your brain. It'll shock me now.
No, that's wrong.
It's wrong?
Sorry.
Okay, what is it? I'm not. You drive me nuts, but I'm not judgmental.
Trying to test you to see if you can catch the error.
Yes. I can test myself a lot. So this, how much? 2779. Okay. First, you don't have to test me. I always test myself. Self-tested.
Well, I thought I tested your patience as well.
Patience is good. The same thing, guys. Secondary current, but this time coil. Now, our people, you guys learned with my friend Mr. Ryman, the I secondary line equal I secondary coil for a Y system, right? So in this case, what do you guys think the I secondary coil would be? 2779 amps. Why? Because it's a Y. It's a star or Y, right? What comes out of the Y, it's going to go through the line. What comes out of the delta, there's every time you have an intersection, it's going to be added to other currents. Right? Delta Y is just going one-way street. It's the same current. At least that's how smarter than me one guy explained it. The current comes out of here. Where is it going to go otherwise? It's just going one-way street. If it's a delta, there's fork. Okay. Now up to this point, everybody's going to get in here, right? Right? We're cool? Okay. It's straightforward. Number 5. Number 5, my friends, is we need primary feeder. Primary feeder. Now, a lot of people, my friend, when it comes to sizing conductors, you drop the coil altogether. For us, the construction people, the manufacturers of the transformers, they use the coil to size the leads. We're not sizing the leads here. So, in this case, I want to assume it's continuous load, 1.25. That's because I'm assuming it's continuous load. That's what I want you to do, guys. Multiplied by I primary line. So 1.25, multiply this by 1204. If I did my math right, you end up with 150. 5 amps, 1505 amps. Right?
Yeah.
Okay, and then we need to size them. I want to size it. Obviously, we're not going to find a conductor that can go that high. So I want to run, this is just the amps. The second one is the cable. You take 1505 divided by 4. Why 4? Because I decided to run 4 sets. You decide tomorrow to run 6 sets, be my guest. Okay? So that will give you 376 amps. And if you go to 310.15 B16 under 75-degree column, the lady that got married and changed their name, you're going to end up with 4 sets of, we're going to carry, how many conductors? It's delta. So it's 4 sets of 3 conductors. Each one of them, I size these, each one of them is 500 kcnm. You guys see why I chose 4? Because 4 gave me the 500. Can I choose 6? Yeah. When we parallel, always hover around the 500. No more than 500. And also, you don't want to parallel 1/0, multiple 1/0. It's a lot of cable. Hover around the 500. See if you can get an amp. A 500 can give you 380. So when you, whatever you divide, try to get you 380 amps so you can cover it with 500. 400 may be good. 600 stretch it a little bit. So, but don't go 1/0 here. I wouldn't go parallel 10 1/0s, for example. It's a lot of money to put cover. Remember, every time you parallel a set, you have a conduit, you have contractors pulling a conduit, the wires. So, any question, guys? Piece of cake. Up to this point, Oladipo's went down to B. Because tomorrow he's going to parallel 12, and he's going to end up with number 1 conductor, which we can't parallel number 1. Let me know when I can go to the secondary, guys. Back, good. Second row from the bottom, good. Oladipo. We need a few time. If you can give me a hint, guys, when you're done, and I'll be very thankful. Yep, yes, no. Cool. First, okay, Olibo. Thank you. Number 5. Number 6. Number 6, guys. And I want to go prime fuse. Primary fuse. Primary fuse. Do you guys remember what we did for the fuse? Primary. Did they say primary feeder? Okay, I'm sorry. I lied to you. I just want to follow my convention here. 6 actually I did here. Number 6 here, just so I don't get confused. 6 I have secondary feeder. Secondary feeder. Okay. Secondary feeder, the same thing, guys. We're going to take a 1.25 multiplied by the secondary conductor. In this case, they're the same. What was the secondary conductor, Aldepo? My calculation is wrong here, I know. 2779, at least the one. Can somebody give the calculation for me here? 1.5 times 2779 equal. Oops, that's a lot of amps. I have 169, right?
No, 3474.
No wonder why I'm 1.25. I see what it is. Times 277.9. Yeah, 3474. 3474 amp, right? Already put. Thank you. Now we're talking. Now with this, okay, now how am I going to parallel these? Let's go divide them by, how about if I divide by 10? That will get me 500. Look at that. If I divide by 10, just by looking at it. So you take, this is, I need to parallel. So I have 3474 divide by 10. You're going to see why I'm going to divide by 10, because that will give me 347.4 amp take it to the lady, she got married, 310.15, B16, 75 degree column. And then that will give me 380, that will give me 500, right? So 10 sets of, I'm going to have full neutral, 4 conductors, 500 kcnm. Now tomorrow, if you guys put 12 sets and you end up with a different size, that's okay, that's right. But everybody knows why I picked up like 347, that will give you 380, 500, very, I love it when I handle a 500. 500. Okay, that's a piece of cake. Number 7. Number 7 is main bonding jumper. Main bonding jumper. And by the way, main bonding jumpers, you guys remember it came from 250.28D1 and 250.66. Right? Remember how we did that? Main bonding jumper. The main bonding jumper, Jackson, is the one you take the neutral and you bond it to the grounding grounding conductor, grounding electrode conductor. Over the size, that's a main. That's a piece of cake. If you guys remember how they do it based on these two articles, they take the 10 and they multiply them by 500. Okay, that will give me a 5000. How many zeros? K, right? 5000 kcm. And of course, this is 500. Another 0. Kcm is larger than 1100 kcm, right? Then what do you need to do? Because remember that rule? 12 and a half, which is 0.125, multiply it by 5000K. Okay? So then you have to use a 12.5% of the. Everybody's following me? We went through that one when you say when you parallel, if you have parallel sets, you multiply the size by how many sets you have. 10 times 500, that'll give you 10,000, 5,000. Then you take 12.5% of the total, and that will give me, Chris, I will depend on you for that one. What's 12.5%?
65.
65?
625.
That's mixed 6, 2, and 5 kcm. And then 625 kcm. You take this one, guys, to table number 8, chapter number 9, NEC code book. Do we have 650? I don't think we have 650 kcm. Anybody check? We have to go to 700 kcm. If I don't know, you're going to go check it. I believe we have 700. So we need 700 kcm. How many of them? Only one. Can somebody check it from table number 8? I don't think we have 750. Maybe I'm wrong. Well, why did they go by the, why did they go to, do I have 650? I'm sorry, 650? No, 650, so 700. And there is no size 650. Because you're going to go to the next standard, Chris. The next standard, I don't think there's 650.
No.
I doubt that it will be.
7 to 750.
From 7, there is 750 though. But there's no 650, but I have to go to the next standard 750. Any question, guys? Piece of cake. All what you have to do is just eat it. Oh, I mean, cake, we're supposed to be on the diet, sorry, Nick. Piece of banana. All right, can I go to number 8? First, table 8, chapter 9.
Go to chapter 9 and you find it.
Yeah.
The order that you know.
Table 8, chapter 9, table 8. I see what you mean. It's right if you look at it from right to left. what do they call this? Dyslexic?
Dyslexia.
Dyslexic, yeah.
Yeah, it means you don't get a Lexus. Dyslexia.
8. Number 8. Number 8. Number 8, my friends, grounding electrode conductor. 250.66, no problem, Chad. We do the same calculation, guys. We end up 10 times 5 K equal 500 K. There's another 0. KCM. You take the 5000 KCM, take it to table 250.66, and right there tell you the largest that you can pull is what? 3/0, right? If I remember right, the largest that you can pull, regardless of the size, is 3/0. Done. Exactly the same like the bonding jumper, except you stop at 3/0. You don't have to move anywhere else. Okay. Number 9. Primary overcurrent protection device, and I'm using a fuse. If you guys remember, for transformers, you go to 450.3B, 450.3B, because the primary and the secondary are less than 600 volt or less. You go to B. If it's A, one of them is more than 600, you go to 450.3A. Okay, if you guys go there, you're going to see that multiplier is 2.5 times at 1204. That will get me a healthy 3010 amp. That's the amp that you get. And if you go there, also tells you there is no node number 1. Means you can't go up. So what do you need to do? Like we said before, you go to the bar, drink, and get mad, or go to the next standard down. So 3010 240.6 get you a healthy 3000 amp. Healthy 3000 amp. Why didn't I go up? If you guys go to the table, it doesn't tell you to go up. There's no node number 1 that allows you to go up. So you can't go up. So you have no option. You can't stay where you are because you can't have a fuse size the same. So you have to go down. Number 10 and the last one. Oops. The one before the last. What do you guys think we're going to do secondary now? Secondary overcurrent protection device, aka fuse. We're using fuse. If you guys go to the same table, if you go to the same table here, it's going to tell you multiply by 1.25. 1.25 times, that's what I need Oladipo to, or Chris to give me. What was the size on the primary? Was it 347? No, it was 2779. Okay, 2779. 2779. And I need a calculator handy. 1.25 times 2779 equal, we did that math before, 3474. 3474 amp. In this case, guys, if you go, there is a node number 1. So you can go up. Why to go up? Because node number 1, 3474, take it to the 240.6, that will get you a 4000 amp. Unless you want to go adjustable circuit breakers, you're going to use 4000 amp. Everybody knows why we went up on the primary and the secondary, down on the primary? The note says if you don't hit a standard, go up.
Oh, on the secondary.
On the secondary.
On the secondary.
Yeah, not on the primary. Yeah, yeah. From the table. Nothing that I wrote right here is from my basement yet. Okay, the last one is 11, guys, when you have a chance, is where the short circuit, the impedance. Let me know when you're ready. Good. 75 degrees, good. Okay. 11 is secondary short circuit. If Chris takes phase A, phase B, and phase C, tie them together with a big bonding bonding jumper right at the terminal, and turn the switch on. How much short circuit are you expected to see? That's what the short circuit at the secondary. That's easy, piece of cake. I short circuit always equal I secondary line over Z impedance. Otherwise, Chris is going to be yelling at me. Z in the impedance format. Z in the impedance format. We just calculated that one. What was it? 3. What was the secondary again?
And that is the adjusted.
No, not adjusted. The raw. 3. Before you multiply by 1.25, what was it? 377? 4?
277.
779.
It was 2779. 2779. 2779. So a 2 and a 7 and a 7 and a 9 divided by, what's the impedance? For this baby, it's given as a 0.04, which is 4%. On the nameplate.
Code reference.
Not there.
Yeah, that's fine.
Yeah. I have to think about it. Yeah. Okay, so if you do the math, I didn't do the math of this one. Can somebody do that, please?
Oh, 70.
70 km. So when you size you guys remember when Todd was here and Jerry, they said then you go size your overcurrent protection device to handle 70 or more. Big deal. Did you guys remember when Todd was here and he showed the difference between the same circuit breaker at a different short circuit rating? The price difference is substantial. So that number might not mean a whole lot to you now, means a lot to the cash flow. Okay, that's question number 1. Oops. This is B. The second thing applies to Miss B. Miss B, the load calculation, guys, commercial load. Do you want to take a break or something? No? Shouldn't take much. It's a commercial load. Commercial load. Everything is a commercial office building. Commercial load, office building. Office building. Inside this office, you have the following. There's a bunch of loads here. We have 15 horsepower. 15 horsepower AC units. 1, 2. Let's put the heater. Heating load. My heating load equal calculated at 150 kVA. These are all calculated. Heating load. 3. I have a 50,000 square foot building. The building is 50,000. 4. I have a sign in the building. 6. These are different loads that we have. Sign. 1 sign. So 6. I have track lights. 200 feet of a track light. Yeah, I'm sorry. Track light.
4 is the side.
Sign. Yep.
5.
5 is 4 is a sign. Ah,
Oh, you don't like 5?
that's 5 is the sign. 5 is the sign. 6. Thank you. That's what I thought. 4 is a sign. 5 is a 2000 track light. 200 track lights. 6, one sign. Yep. 6 is 50 foot of multi-outlet assembly. Multi-outlet assembly. Multi-outlet assembly. Multi-outlet assembly. 7.
Is that continuous or non-continuous?
Non-continuous. Yeah, unless I tell you it's continuous, it's always considered non-continuous. Okay. 10 is 7. 7 is 250 receptacle. There is 250 receptacle. And where are we here? 8. Don't have 10 maybe, Chad. 8 is 10 circuit. Each one of them is 20 amp. And they are for computer load and continuous. These are dedicated for data, continuous. Okay, let me repeat. This is the building that you have. I don't want you to put the code references for them, guys, because we went through this in details. We're just going to do the math on that. Let me go over it one more time. I have a 15 horsepower AC. Heating load is given as 150 kVA. I have a 50 square foot building, okay? And I have a sign, one sign, 200 feet of track lights, 50 multi-outlet assembly non-continuous, 250 receptacles, and number 10 is 10 circuits. Each one of them is 20 amps. And oh, by the way, the voltage of these are 120 volts, because you need the voltage. 120 for computer load, servers, continuous. We need to calculate the following. The service. So we're going to size the service for this.
Oh, the motors, what are they?
Burning at. What's the voltage?
Yeah.
Yeah. Well, that would be interesting if we know the voltages. Otherwise, how are you going to do? It's a 480 system. The voltage on this is 480. The voltage for the equipment is 480. Otherwise, yeah, Chad, how are we going to? You can run this at any voltage. 480, right? Number 1. Number 5. Okay.
Oh, and that number 1, is that, air conditioning, or is that?
One of them is air conditioning, one is heating. So you're going to choose the largest of the heat or cool.
Okay.
That's what we're going to do. Okay, let's go do it. Go ahead and everybody got that info? We're just going to go size the service for that, baby. That's it, just the service. So I'm going to start, guys, with the lights. I'm going to start with lights. Let's do the calculation for lights. Anything that light. Do you guys remember general light? I have. We don't have any fixtures, do we? We didn't give us any. They have a track lights, but they didn't have any fixtures, any general purpose fixtures, right? We have a track light. Track light is different than general purpose fixture. So how many fixtures do I have? I don't know. So we're going to use the table for lighting. I will say first one is general light. Since I don't know it, the code allows you guys to, if you remember that, you take 1.25 and you multiply it by 3.5 and you multiply it by 50. That's for 50,000. Remember that the square foot of the building multiplied by 3.5 from the table times 1.25 because it's continuous. That should give you 219 kVA. That's the general one. Because I don't have fixtures. If I have fixtures, I have to choose whichever is larger. Everybody knows where the 3.5 came from? This is, I don't want to go referencing this piece here as that piece here as from 220.12. 220.12. Table 220.12. Okay. That's A. B. Track lights. Let's do the track. Also lights. Track light. The track light, guys, I have 220.43b. I hope somebody will verify that one for me. 220.43b. Anybody verify that one? If you guys go there, it says for every 2 feet, multiply by 150. So piece of cake, Chad. 1.25 because continuous load. All lights are continuous load. 200 because that's how many we have. Multiplied by 150 from the code. Divide by 2 because the code says for every 2 feet, give it 150 kVA, 150 volt. Okay? Cool. And I'm going to make the answer directly in kVA. So when I did that one, if I can know how to read my writing, 19 kVA or 11 kVA, Chad? Anybody did the math on these? I have 11 kVA. Oh, no, 19. 19 kVA. The reason why I convert to kVA because I'm dealing with kVA. Everything is kVA. Okay, anything else light? A, B, C. The sign also light, kind of. Sign. For the sign, guys.
Do we need to know what the voltage the track lighting is?
No, not this one. No. For the sign, I think 220.14F. 220. I have 14F. Anybody verify? I have all these reference for you guys when we did the math. By the way, for the test, I don't want you to write the references. We already have them in our other calculation. So if you guys go there, it says 1.25 times 1200, and I'll get you 1.5 kVA. For this baby, right? For this baby. That's for the light. Remember, this is my light. The second load is heating, cooling. Heating, cooling. The heating, cooling / cooling of the building, guys. The heating is so easy. Heat is already given at 150 kVA. The cool is the issue. The AC, for the ACs, AC, I have 15 horsepower. I need to go the full load amp. If you take this one to 430.250 cable under 460 volt, you will find it 21 amps. 21 amps. It gives you 21 amps. Okay, then you do your math. You're going to take 15, because there's 15 of them, multiplied by 1.73 times 21 times 480. These are to find the kVA for the motor. That will get you 261 kVA. So which one do you think I'm going to use for this? The heating or the cooling? The cooling, thank you. So I'm going to be using this number to carry downstream. Don't forget that also, guys, I'm going to be using this number here to carry downstream. I'm going to be using this number here to carry downstream. And also I'm going to be using this number here to carry downstream. All right, we're going to add them all up. When they say carry downstream, we're going to add them up. These numbers that I put a star next to them, we're going to carry them downstream. What else do we have? Computer load. Any question? Let me know when you guys are ready. everything that I circled here will be added later on to find the surface. And you know why I picked up not the 150, the 261. Everybody knows what I did here. I just converted the horsepower into volt amp because I need to compare apple with apple. I can't compare apple with oranges. I can't compare horsepower with kVA. You have to cache the horsepower to kVA so you can compare. If both of them are horsepower, it's so easy. And then also you have to cache them from horsepower into kVA so you can add them to kVA. I can't add 3 Chris's and 2 Chets. That doesn't make 5 watt.
That makes a bit, right?
Oops. No. You have to add a different
Oh, okay.
gender to make people.
So 745 watts per horsepower.
Now we're going back to the volt amp. Yes, sir.
The 15 on the bottom down there, that comes from horsepower.
The 15 here is how many of them? I have 15 of them. Oh, yeah, that 15. What is this 15 here? I should have used a different number. Gosh. These 15. 15.
Power at
15.
1500 kVA.
Yeah. This first 15 is the number of AC units. It's a bad choice. I have agree with you. I owe you an apple. Yes, what's wrong with that?
Well, I think you said really.
An apple, like an apple to eat. Not computer apple. That's Gary Ryman, right? Okay, the second one, guys, is computer load. Computer load. All what you need to know about this baby is continuous. That's it. So how many circuits do I have about this? I have 10 circuits. Each one of them is 20 amps. Each one of them is burning at 120. And it's continuous. I'm going to push a 120 inside them. So, what do you get? 30? 30K? 30 kVA. Don't highlight this one because I'm going to carry this. Right? Did I do it right? I have 10 circuits, 20 amp each. 120 is the voltage. And I multiply by 1.25 because it's 1.25. Equal 30, right? Okay. All right. The last thing is receptacle load. Load. Okay, let's see what we have for receptacle loads. First of all, we have the general purpose receptacle. The receptacles themselves, how many do I have? We have 250 multiplied by 180. They're non-continuous. So that will get me 45 kVA. Okay? Did we say we compare the multi-out assembly with them? Is that what we discovered last time? You were complaining about that one, Chris. The multi-out assembly 220.14a. Let me just check that one. 220.14a. It's been a while. 220.14. What did this? 220. Where am I here? Multi-out 220.14h. That's why. Okay, multi-out assembly. Willing. Multi-out assembly. Okay, we got that one. Okay. .14i. Okay. 14. Or okay. Or the one per okay, so that doesn't include the it. Okay. So that's the first thing. The second thing I want to do So we get this one. This is coming from 220.49. This is 220.14i. Okay? Then this is the receptacles. The second one, guys, is multi-outlet assembly. This is going to be coming from 220.14h. This baby, it says if it's non-continuous, you take them, divide it by 2. For every 2 feet, assign 180. Okay? There's 50 of them, right? For every 50, divide every 5 of them, not 2. For every 5 of them, assign 100. For every 5 feet of that multi-out assembly, if it's non-continuous, assign 180. So if you do that, that'll give you 1.8 kVA. 1.8 kVA. Cool? Also, demand I want to say code. This is NEC code. Since it's an office building, guys, you have to do this step, which is 1 times 50 kVA. 1 times 50 kVA. That will give you what? 50 kVA. This is from the code. You have to choose. Since it's an office building, you're supposed to choose between this number and these two numbers. Which one of them is the largest? 45 is the largest. No, I mean 50 is the largest. Look at how you look at me. You're going to compare this number with the actual design. So 45 is the largest. 50 is the largest. Then you're supposed to take the 1.8 and derate it if it's more than 10K. Is 1.8 more than 10K? So there is no derating involved. Yes, sir.
Yeah.
Thank you. This is 220.14K. This is from 220.14K. If you guys go there, it will tell you you have to do that 1 volt amp per square for an office building, which this is an office building. I'm telling you.
So you don't add the multi outlets to the higher of the other two and then derate?
Okay, in Bank's office shall be calculated to be the largest of 1 or 2, as calculated by this or calculated by 1 volt per square foot. And okay, you're going to use then. I'm sorry, say it again.
Wouldn't we take the greater of the two, the receptacle count versus the code, then add the multi-outlet
Yes.
assemblies and then apply the derate?
No, you don't apply the derating though. After you choose, it's the largest of the two. You apply the derating for the receptacles. You apply the derating for the receptacle, the number of receptacles. We're supposed to apply the derating for the receptacles. The derating.
So only for installed receptacles.
Yes, absolutely. Only actual install. Okay.
So then you add the
Receptacle loads in according with, if you look at 220.44, it says receptacle loads calculated in according with H and I. Where is H? The multi-out assembly and I, which is the receptacle, shall be derated. So you're really in reality going to add these one and derate them, but I know just by looking at it that 50K is larger than both of them. So I don't need to do the derating, right? So what's the step that I'm going to be carrying from this? 50K, right? 50K. All right, so the last thing, guys, is adding them all up. I want somebody to give me total load. which is this is the first thing I'm asking you for to find, guys. Demand. It's called demand load. Find the demand load for the whole building. So what am I going to do? I need somebody to copy all these numbers for me. Aladipo, you're going to go start from 219. Okay, can you guys give me?
Get a number.
Can you give it to me so I can write them down? So, thanks, bud. Okay, let's start with, what was it? It was 219 plus.
19 plus. Okay, you go live. You got it.
One of you guys going to go?
19?
219?
Yes.
Uh-huh.
Then 19.
19?
Yes.
Uh-huh.
19.
Yeah.
Oh, okay. 1.5. 261. 30. 45. 1.8. And then 50.
Oh, what's the answer?
I got 627.3 kVA. 627.
27. Anybody came up with something different?
I thought we were thinking like 45 and 1.8, just down to
Yeah.
Oh, thanks.
Oh,
Thanks, Bill.
yeah, this one is, I thought it's coming from a different load. Yo, the largest of the two.
On the 1.9.
And the 1.8 too?
Don't we add the 1.8 though?
The 1.8, the 1.8 we have to add. The 1.8 we have to add. Okay, what's the,
So now we're at 582.
so what is that?
582.
582 kVA. Anybody came up with something different? Anybody came up with something different? Okay, that's the first thing. From here, very easy. When you reach this point, piece of cake. Can I go to the next step when you guys have a chance? Yeah. We just added all of them up. The 50, don't forget the 50 and the 1.8. Can I go? Chris?
yeah, I'll talk to you.
Okay. Let's go to number 2, guys. Number 2, we're gonna find demand current. Demand current. The demand current is I. Take the what was the number that we have? We're gonna take the 582. Let's take the 582K divided by 1.73 times 480. I need somebody to do the math for me here, please. You guys come up with 700? 701? Yeah? Anybody came up with something different? You come up with something different? 701. 701. 701 now. Okay, number 3. That's easy from there. Standard panel size. The panel size, you're going to take the 701 amp. You're going to take it to the panel, guys. We're going to go to D wall. Remember that the panel size. We're going to use D wall for the panel size, which 3. Okay. This is Okay, so I have 3 wire up to 600. I have to flip. So switch boards. I need to go to DeWalt. The page is 3-13. And if you guys go there, the panel, not the overcurrent protection device, the panel size is going to be an 800 amp. The panel size is 800 amp. That's just the copper, based on DeWalt. Okay. Number 4, overcurrent protection device size. Same thing, you take the 701 amp, take it all the way to 240.6. Now the next standard, guys, if you do that, the next standard, either you can go 700 or 800. Look at the jump, 701 all the way to 800. Let's do it. That's where you use your judgment. Would you like to jump for 1 amp all the way to 800 amp?
Actually, if you use the square root of 3 rather than 1.73, you're under 700.
Are you? Okay. So let me just, can I just use it literally? And if it's higher than the next standard overcurrent protection device would be what? 800 amp. Though you might have to use your judgment here. You might say, well, you know what, Chad, I'm going to put 700 and I'm going to eat that amp. Okay, done, almost. So the feeder, number 5, panel feeder. For the panel feeder, guys, I'm going to have 800 amp divided by 2. I'm going to have 400 amp, right? This one, you can, for an 800 amp, 400 amp, you can do a following. I'm going to take it again. I'm going to say match, by the way, match overcurrent protection device. So that's what I did. Then if you go to 310.15 B16 under 75-degree column, you're going to have 600 in it, right? We're going to have two sets of 600 kcm. How many? 4 conductors, because I decided to pull full neutral since I'm not paying for it. This is an exception in the code, actually, that sometimes they allow you to use 2 sets of 500, guys. So if you see it, 2 sets of 500, don't say that Chad did it right. There's an exception in the code up to 800 amp. They allow you to use smaller conductor. But let's just go literally match it to the table. You need 2 sets of, at least for me, 2 sets of 600. Okay, the last thing. Can I move, guys? Last thing. Number 7. Number 6. Oops. Now it's number 6. Number 6 is I need to find main bonding jumper and grounding electrode conductor. So I'm going to start with grounding electrode conductor. 250.66. There were 2 sets, right? 2 times 600 K equal 1200 K. Then you take 12.5, 0.125 times 1200. Right? This is more than 1100 kcm. So anybody can give me the answer? 12.5. 0.125 times 1200. 150. 150 kcm. They don't have a 150 kcm though. 150 kcm. Take it to, now I'm going to do it in order. Chapter number 9, table number 8. That will get me, can you guys go there and see what you get? Chapter 9, table 8. Riyadh, we'll trust you. You get 1 conductor 3R. I'm sorry, this is for the main bonding jumper, guys. This calculation is main bonding jumper, okay? Grounding electrode conductor, same calculation, except you take the 1200 kcm to 250.66 table, and the largest that you can install in this system is one conductor, 3-aught anyway. So they end up being the same in this case. And you can see why they were the same. We're very close to 1100 kcm. Any question, guys?
Yeah, where you got 600 from? Where's that?
Oh, these are the conductor size.
Well, we divided it by 2 to parallel it.
That's that conductor size. When the two is the two sets, right? That's it. Now, by that time, Tom, my friend, you got all the way down to D+. Oops. Your test tomorrow, guys, will be very similar.